started. So we will celebrate Thanksgiving by having Sourav Chatterjee tell us about the Higgs mechanism.
Okay, thanks, Akshay, for the invitation. It's a great honor to be here, really. And so let's start with what are quantum Yang-Mills theories. I'll assume that nobody has a background, although I know that various people in this audience have a lot of background, but in these things. But I'll just do nothing. So these are the building blocks of the standard model of quantum mechanics. And these quantum theories are in Minkowski space, which is our space-time, but they're analogs in Euclidean space known as Euclidean Yang-Mills theories. And physicists believe that the calculations in these Euclidean theories can be carried over to quantum theory. So this is a whole constructive QFT program which aims to justify this mathematically, although it's not fully developed for Yang-Mills theories. And these Euclidean Yang-Mills theories are supposed to be classical statistical mechanical models of field theories, which make them, probability models, okay? And the problem is that in the continuum, we don't even know how to construct these classical theories in a rigorous way, mostly. And for most of these theories, we don't know. So what we'll do instead is what are called these lattice Yang-Mills theories, also known as lattice gauge theories. These are discretized versions of Euclidean Yang-Mills theories that are mathematically well-defined. So there is no problem in defining these theories. And the next few slides, I will define lattice gauge theories. So these theories model the behavior of three kinds of fields in general: gauge fields, boson fields, and fermion fields. And I'll not talk about fermion fields in this talk. I'll talk only about theories with gauge fields and boson fields. Okay. So just as an aside, before I start the talk, let me tell you a little bit about I'm in probability theory, and what am I doing here in this area? So it actually it's due to Akshay. So several years ago, 2014 or 15, sometime like that, we went for lunch, and Akshay told me that Yang-Mills theories. I said, yeah, I've heard the name, but what are those? And he said they're basically probability models. So then I started thinking about it, and then I wrote some papers, and then other people joined, and now probability, lots of probabilists are working in Yang-Mills theories. And it basically began with this lunch meeting that I had. So thanks to Akshay, there's this big area now in probability theory that's who are working in Yang-Mills theories. So some examples, I did this, wrote this paper a while ago on rigorous solution of strongly coupled SON theories. I showed that there is this rigorous gauge string duality that you can establish in these discrete models. Some calculations can be done using dual calculations in the lattice string theory. And then this more recent one, I proved this physics heuristic that something known as unbroken center symmetry causes confinement of quarks. It's a conditional theorem which says that if there is unbroken center symmetry, then quarks confine. And so anyway, but today I'll not talk about any of that. So I'll talk about work done since coming here, and it's still going on. And in the last week, I gave a talk in Avi's seminar, and that was also work done here. So I've been having a really wonderful time since coming here, and talking to Tom and Ed Witten, and it's been extremely fruitful. So I'm really glad to be here. Okay, so let's come to the model. So what is a pure lattice Yang-Mills theory? Let's start with the pure lattice Yang-Mills theories without Higgs fields. These model the behavior of only a gauge field without any Higgs field or fermions. So you start with the compact Lie group. This is called the gauge group of the theory. Let lambda be a subset of the lattice, z to the d, where d is the dimension of space-time. So the most important case, obviously, is d equals 4. So we'll take lambda to be this cube, minus L to L to the power d, where L will eventually be sent to infinity. Let E denote the set of edges that are oriented in the positive direction. So x, y, directed edges, where x is less than y, the x is directed order. And the space of gauge field configurations is G to the E. So a configuration is an assignment of group elements to edges. So on each edge, you have a group element, and that's a configuration. And I will tell you where this comes from in relation to the continuum theory, the way that physicists usually talk about, in continuum theory, in theoretical physics where this comes from. Okay. And we'll denote configurations like this as U, which is U subscript E for each directed edge E. And if you take an edge oriented in the negative direction, so if you have a positively oriented edge XY and the negatively oriented version is YX, then UE prime will be just an inverse of UE. So if you look in the negative direction, you just take the inverse of the matrix. Okay. Any questions about this? What is the configuration, or what is the space? Because the thing is, I'm sorry, but there's a whole lot of things to introduce before I can even talk about some results. So please bear with me. It's not something where I can quickly go into the result. So there's some notational heaviness here. So anyway, we start with this.
So n is one coordinate increased by
one coordinate, it just increases by one. Nearest neighbor edge. So one coordinate increases. So that's the directed edge. Okay, so the next thing is plaquettes. A plaquette is a square bounded by 4 edges. Okay. So given a configuration U and you take a plaquette P bounded by 4 directed edges joined end to end. So you go like maybe in an anti-clockwise direction. So E1, E2, E3, E4. And you define UP as just the product of these matrices along these 4 edges with the appropriate orientations. And there is some ambiguity here about the choice of the first stage in the direction of traversal. These 2 things we have to choose when you define this, but this will not matter because we'll only deal with quantities that are not affected by these choices. So I'll just let this ambiguity remain. And I define given U, given a configuration U for each plaquette P, I define UP like this product. Okay. Clear. Remember, UE is only defined for positively oriented edges, but in these 4 edges, 2 will be negatively oriented, 2 will be positively oriented. So we take inverses of those. Okay, so how do you define the lattice gauge theory? You choose a number G0, positive number called the coupling constant of the theory. Let rho be a finite dimensional representation of G and let chi rho be its character. So you take the trace. The action for our theory is this. So you take a configuration. For each plaquette, you compute your UP, take chi rho of UP, and take the real part of that. So this whole thing is not affected by these choices of which is the first edge and in which direction do you traverse, because the real part takes care of the direction, and the trace takes care of the starting point. So it doesn't matter. And you sum overall plaquettes and divide by this 4G0 squared. And traditionally it's denoted by G0, so I've kept this notation. So there will be no G1, G2, and so on. So we'll only have G0, but I'll keep that. Let sigma denote the space of gauge field configurations. So our lattice gauge theory defines the following probability measure on this space, which is you take e to the power this action and put that as a density in front of the product Haar measure. So I'm taking the normalized Haar measure here. This is a probability measure. So you take the product probability measure on this configuration space, put this density in front of it, and then divide by something appropriately so that it has probability mass 1.
Is this going to be sensitive to rho, or can I just imagine it's a standard representation?
So you can take the standard representation. So yeah, so you can. But later on, there will be some other representation which will not always be the standard representation, where I couple the Higgs field. So typically here, this one is taken usually to be the standard, or as a phase is say fundamental representation.
So what is a gauge? What? Do you have some gauge invariant?
Yeah, so I'll come to that in a minute.
Are you taking periodic boundary condition?
So right now I'm not taking periodic boundary condition, but later on I'll take periodic boundary condition. So right now I'm not going to that computation. So just define it. This is free boundary condition.
What kind of G should we be thinking of? Anything? But what in the end?
The group. So typically, in physics, the most important groups are SU3, SU2, U1. But U1 is abelian, which is easier. But SU3 and SU2 are the most important groups. But there are other theories which take SU5. But typically, small dimensional groups. But there is also a branch of this theory where you take SUN and going to infinity. But that's a different kind of theory.
Normalized R method, this means volume 1.
Volume 1, yeah. So it becomes a probability measure, so that it's a probability measure. And yeah, the Haar measure means volume 1. Yeah, normalized Haar measure is volume 1. Yeah. Okay. Other questions? Is the definition clear? So that's pure lattice gauge theory without Higgs fields. Okay. So typically, the integral of a function f with respect to this probability measure is denoted by this angle brackets f. That's standard notation. So what is mass gap? Very roughly speaking, a statistical mechanical theory is said to have a mass gap if it has exponential degree of correlation. So if you go to a quantum theory, it's related to the eigenvalues of the Hamiltonian. But if you translate it to the statistical mechanical theories, you can just think of it as exponential degree of correlations. What does this mean? Again, roughly speaking, if f1 and f2 are two functions from the configuration space into the complex plane, such that f1 depends only on the values of u at a certain small collection of edges, you can think of u1 as maybe 5 edges or 3 edges, and f2 depends only on another small collection, and these are disjoint subsets separated by this distance, so you can take this as some kind of graph distance or maybe even Euclidean distance. Then the expectation of the product minus the product of the expectations should be bounded by something decaying exponentially in the distance between the sets. So that's exponential degree of correlations, and you can take that as a definition of mass gap when I say the theory is massive or it is gapped. Okay. So the reason why it's called a mass gap is because with appropriate choices of F1 and F2, we can relate the masses of particles in the theory with the constant C2 in the exponent. And this is why these theories are said to have mass. And there are actually groups of people who do huge simulations with lattice gauge theories to actually estimate masses of particles. And those are much more complicated theories than what I stated here. They have a lot of components, but they run these simulations, try to estimate these this exponent in this exponential decay and estimate the masses, and they get good agreement sometimes with experiment.
If you have such decay, will it be a C2 which is always the same for bigger and bigger distance?
Yes. So so C2 may not depend on the size of lambda. So that's so you have this theory, and this is when it's called a mass gap. But we'll consider later on. We'll consider these parameters. So I've shown you one parameter G0. There may be other parameters, and C2 may depend on those parameters, and those parameters are sometimes varied with the size of the box that you're considering. So in this case, C2 will vary, but other than through the parameters, it shouldn't be depending on the size of the box. Okay, so now what are some rigorous results that are known? So using this cluster expansion technique, it's one of the foundational things in this area and other areas of statistical physics by Glynn, Jaffe, and Spencer. It was shown by Osterwalder and Zeiler that any pure lattice Yang-Mills series is a mass gap when G0 is large enough. So if you take G0 large enough, any dimension, you will get this kind of exponential decay of correlation.
Mass gap means independent of the size.
Independent of the size of the box. Yeah. Independent of the size of the box, you will get a decay of correlations. If G0 is large enough meaning, again, just depending on the gauge group and the representation, but not on the size of the box.
Yeah, sorry, I forgot. Was the action, does it have 1 over G0 in front of it? Or
1 over G0 squared.
1 over G0.
Yeah.
It's like a high temperature.
Yeah.
Still about TC2. Will it be the same if you go into the direction of one coordinate or something skew? So is there some conformal invariant?
No, not that I know of, unless you go past your continuum limit. So right now I'm just talking about this discrete theory. Yes. And the discrete theory, if G0 is large enough, then it doesn't have sort of continuum behavior. The exponential decay will fall off sharply. And the correlations.
It's not only sharply, but in an isotropic way.
Yes, exactly. So this is known as a strong coupling regime. So when G0 is large enough, that is, the coefficient in front of the action is small enough. However, I'll come back to this later on. The real world corresponds to small G0. This is known as weak coupling, and in particular G0 tending to 0. So for example, if you consider in 4 dimensions, pure U1 theory, if the gauge group is U1 and you consider, without any Higgs field, this is a theory of photons, and it's massive at strong coupling, but that doesn't correspond to reality because photons have no mass. And so the weak coupling is the one that corresponds to the real world. Okay. So the challenge is to understand these theories at small g0. Any questions about this? If you want to look back at something, let me know.
Yeah, can you do the U1 theory not in a lattice?
Yeah, so the U1 theory, there is a lot of literature on the U1 theory. You can do it in the continuum, and so you can develop U1 theory in the continuum, and there is.
And does it relate to the U1 theory in the lattice?
You can. So there are some results which prove that the U1 theory on the lattice converges to the U1 theory in the continuum, but I don't know if that is completely satisfactory developed in dimension 4. This convergence. So 3 dimensions, I think there is a satisfactory.
So things are more difficult or easier in higher dimension?
So dimension 4 is supposed to be the most relevant and the most difficult case. Okay, so yeah. So I haven't seen so much work in higher than 4 dimensions. There's a lot of work in 2 dimensions. 2 dimensions, Yang-Mills theory is more or less well developed, and due to a lot of work by a lot of people. But 3 dimensions, there is some significant development, but not complete. And 4 dimensions, we have the sparsest collection of results. And I haven't seen so much in 5 and higher among rigorous results. Okay, so what is gauge symmetry? So the next important thing is what is called gauge symmetry. So let theta be g to the lambda. So an element in this theta assigns group elements to vertices instead of edges. And elements of this set are called gauge transforms. And gauge transforms form a group under pointwise multiplications. It's just a power of g, so it's a group, and it acts on our configuration space as follows. So given a gauge transform and given a configuration, the action is defined as follows. So suppose E is the directed edge xy, in a positively oriented edge, we define VE to be theta x UE theta y inverse. Okay, and you can check that this is a group action, and you can also check that the Yang-Mills action is gauge invariant. So if you take theta of u and figure out the Yang-Mills action, then it's equal to S of u, S theta u. So this implies that any gauge transform theta preserves the measure mu defined by our lattice gauge theory. And this is the property, this property is known as gauge symmetry. So in probabilistic terms, what this means is that if you pick a random configuration from this probability distribution and you apply a gauge transform, the distribution of this random configuration doesn't change. It remains the same. Okay, so that's the probabilistic way of saying it.
Now, when your definition of mass gap, do you want your function F1, F2 to be gauge invariant?
Typically, they're taken to be gauge invariant, yeah. And if they're not gauge invariant, I think there is even some theorem which says that if they're not gauge invariant, you get correlation 0 automatically. So yeah, you want gauge invariant functions. Okay. Okay, any questions about this? Okay, so gauge symmetry is considered to be an essential feature of any gauge theory, and a model that does not possess gauge symmetry is unphysical, and I cannot go into the details of this. So this is any physical model should have this gauge symmetry. And, it's hard to construct things in the continuum. So that's one of the roadblocks to constructing continuum models is this gauge symmetry becomes extremely difficult to ensure. But in discrete models, this is very simple. You have this discrete gauge transforms, and you can just look at the Yang-Mills action and check that it's gauge invariant, and that does it. Okay, so what's the Higgs mechanism? So it is believed that gauge symmetry is what prevents certain lattice Yang-Mills theories from acquiring mass at weak coupling. And this was the original motivation of Higgs when he defined this. So Higgs mechanism was designed to impart mass in massless theories by introducing spontaneous breaking of gauge symmetry. So I'll explain what this means. Okay. So it was in the early 60s when Higgs introduced the Higgs mechanism. And so at that time, people were very interested in this electroweak theory, Weinberg-Salam electroweak theory, and theory of the weak force. And it wasn't clear how these gauge bosons were acquiring mass. And so there was, various people proposed various things. And one of the things that was suggested by Higgs is the Higgs mechanism, which preserves gauge symmetry and yet introduces mass at weak traveling. Okay, so what's a Higgs field? Let K be a positive integer. A Higgs field is simply a map from lambda into C to the K. So it's just at each vertex, you have a K tuple of complex numbers. And that's a Higgs field. Let gamma denote the set of all Higgs fields. Then the space of configurations in our lattice gauge theory is now sigma cross gamma. So now you have a gauge field and a Higgs field together. So now you have a bigger space of configurations. It's clear.
And K has nothing to do with its representation.
No. So I'll come to where K comes from, and K is basically how many particles are there in there. So now let sigma be a representation of G in C to the K, which is unitary with respect to the usual linear product on C to the K. So you take a unitary representation of G in C to the K, call it sigma, and let V be a function called the Higgs potential that grows faster than quadratic at infinity. So sometimes, a common choice is what's called this Mexican hat potential, which is norm squared minus 1 whole squared. So that kind of thing. So something that grows faster than quadratic at infinity. And the action is now defined as follows. This was our original action, 1/4g squared, the real part of chi rho up, the usual thing. Now, then there is a term where the Higgs field and the gauge field interact, and they interact as follows. So you take an oriented edge, xy, you take phi x star, sigma ue phi y. So sigma ue is now a k by k complex matrix, unitary matrix, and you take this vector, you take its action on this vector, take the inner product with the vector phi x, and take the real part of that. And there is a parameter lambda here. And then you take minus v of phi and norm phi, and you need this so that when you raise this to the power e, that becomes integrable. So you have a finite integral. And as usual, you define the probability measure mu on this space of configurations, which is now a gauge field and a Higgs field, as d mu u phi, as this e to the s u phi, and then you the base measure you take product of Lebesgue measures for phi, and product of Haar measure for u. So that's a lattice Yang-Mills theory with a Higgs field.
I forgot the notation.
Yeah.
So what is U and what is phi?
So U is your gauge field configuration. So U is for each edge you have a matrix, you have a group element. And phi is for each vertex you have a vector, so in C to the K. And your configuration is these things taken together, sigma cross gamma. And you take your base measure on this space as the product of the normalized Haar measures for the U's and the product of Lebesgue measure for phi. Okay, and then you put a probability density, which is e to the s u phi. S is this action, and sigma is a representation, unitary representation of G in C to the K.
And this capital V is just, things shouldn't depend much on V, is that right?
Yeah, things shouldn't depend much on V. So often it's, in many situations, one takes V to be, constricting phi to a sphere. So it's zero on a sphere. Yeah.
You take it infinite, sort of.
Yeah, so you can do that. Yeah, so you take it infinite outside the region, so you can do that. Yeah. Okay, so we are still,
defining a lot of parameters.
Yeah, I have, yes. So V will be kept fixed. So I have two parameters, G0 and lambda. So
and K.
Yeah, but that will also be kept fixed. Sigma, in that sense, sigma is also a parameter to the representation. But so I'll give you some examples.
So you have two representations, this rho.
Yes, rho and sigma. Okay, so sorry, I'm still defining things. Okay, So some examples, so SU2 theory, if your gauge group is SU2, and you take sigma to be the fundamental representation, so rho I'll always take to be the fundamental representation. So fundamental representation in physics terms, it just means a standard representation. So this representation of SU2 as SU2 itself, acting on C2. This appears in theory of the weak force. So there are, these four fundamental forces, electromagnetic magnetic force and a weak force, strong force, and gravity. And for the strong force, you need the SU3 theory with the Higgs field in the adjoint representation of SU3. Okay, so the fundamental representation doesn't work. You need the adjoint representation. That's what comes in theory of the strong force.
And what do you use for the representation rho, which you are?
Oh, just a standard, fundamental representation. So rho, yeah, in both cases.
In both, but for SU3, it was another one for.
Yeah, so the adjoint representation is for the Higgs. Yeah.
And what is the meaning of these different? Who's choosing these things?
Yeah, so there was, I think it was mostly by trial and error. Okay. And some people, the people who got it right got Nobel Prizes. So that's how it went. So it's not clear why these things work as they should, but it seems to give the right predictions, or almost the right predictions.
And what becomes of the gauge symmetry?
The gauge, yeah, so I'll talk about that. Yeah. Okay, so the gauge transforms. How do you define gauge transforms with the Higgs field? So for a theory coupled to the Higgs field, the group of gauge transform remains the same. It's just one group element to each vertex, but its action is now different. So it now acts on this product space, sigma cross gamma, as follows. So you take a U and phi, you take a gauge field and a Higgs field. You define the action of theta on this pair as follows. The action of on U is just the same as before. So you take an edge E, E is xy, VE you define as theta x, UE theta y inverse. But the action on the Higgs field has a novel definition here. So what you do is you take theta x, you just apply this representation sigma to that, K by K matrix, you multiply phi x by that, and you get this new Higgs field. So that's the action of a gauge transform on this pair, gauge field and Higgs field. And using the fact that sigma is unitary, it's not hard to verify that this is a gauge invariant. So you can check, and there you need that sigma is unitary. That this becomes a gauge invariant function. So again, the theory has gauge symmetry, meaning that the probability measure mu is preserved by gauge transforms. Okay. So this is preserving gauge symmetry. Now, what is spontaneous symmetry breaking? The main impact of this Higgs mechanism is, even though this theory has gauge symmetry, the Higgs field breaks the symmetry spontaneously and imparts mass to the gauge bosons. What does this mean in probability language? It means that conditionally given the Higgs field, the gauge field will have exponential decay of correlations. Okay, so once but often, the Higgs field also has mass, and from that, it follows that, unconditionally also. But anyhow, what this means is that, so I saw this nice analogy on the CERN website that, what is spontaneous symmetry breaking? So suppose you have balanced a pencil carefully on its tip, and you just let it go, then it just falls. So it chooses direction. So it has this perfect symmetry, but then chooses direction. So it's this, once you have chosen a configuration, once you've chosen a Higgs field, given that it makes the theory massive in that the gauge field now has exponential decay of correlations, conditional in that. So is this true? Can one prove this? Okay, so I'll tell you what is known. So as mentioned before, mass generation with and without Higgs fields is known as strong coupling, large G0. This was proved by Osterwalder and Zeiler. So you don't really need the Higgs field. At large G0, there is always mass. So this was further developed in this influential physics paper of Fradkin and Schenker, and they discovered this Higgs confinement complementarity phenomenon, which I don't understand very well. But so this was developed, and more nuanced descriptions were found. Now, at weak coupling, small G0, is well understood rigorously when the gauge group is U1, and this is due to the works of many authors in the late 70s and early 80s.
What is the representation of Higgs
in U1?
Yes.
Yeah, just the usual.
So the same.
Yeah. So it's one-dimensional. It's the one-dimensional presentation. Now, for non-Abelian theories satisfying a condition known as complete breakdown of symmetry, Zeiler proved the mass gap at weak coupling if G0 is small, provided, so he needed a different thing to be large, which is lambda times G0 squared. So if this is large enough, then he could prove. So remember, there are these two parameters here. I'll go back a little bit just to show you, because this is important. So there's lambda and this G0 squared. So 1 over G0 squared is the coefficient in front of the gauge term, and lambda is the coefficient in front of the interaction term, the interaction of the Higgs with the gauge field. Okay. So if lambda times G0 squared is large enough, then and there is this complete breakdown of symmetry, Zeiler proved a mass gap. So Zeiler assumes that the Higgs field takes values in the unit sphere. So VR, the Higgs potential is infinity if R is not equal to 1. So it takes value on the unit sphere. And under this condition, it defines complete breakdown of symmetry as follows. For any Z with norm 1, the subgroup of G which fixes Z, so consisting of all U, so that sigma U Z equals Z, so the stability group, is trivial. And this condition holds for physically irrelevant theories with proper choice of Higgs potential. So with SU2 in the fundamental representation or SU3, the adjoint representation, you can prove with, proper choice of the Higgs potential on the unit sphere. You can prove that this condition holds, and therefore you can prove complete breakdown, this mass gap, if provided lambda times G0 squared is large enough. So now the question is, does this prove the validity of the Higgs mechanism? So pure Yang-Mills theory have only one parameter, G0, which needs to be sent to 0 to obtain theories that correspond to reality. But when coupled to a Higgs field, there is one more parameter, this thing called the squared Higgs length, this lambda. So Zeiler's result requires lambda G0 squared to be large, although G0 can be arbitrarily small. And unfortunately, this still keeps us in this unphysical regime. So I'll explain this shortly. So it still does not prove the validity of the Higgs mechanism. It keeps you in the regime which doesn't correspond to reality. So recall that the Higgs field is said to generate mass if for any F1 and F2, you have this decay of correlations, exponential decay of correlations. And now I'm taking conditional expectation given phi. And the optimal value.
F1 and F2 is function both of the U and of the X, or only of U?
Okay, so I'm just taking only a few for now. So I'm just having this weaker thing where you just prove decay of correlations, exponential decay of correlations given the Higgs field. You fix the Higgs field. And the optimal value of 1 over C2 is called the correlation length. So the correlation length is, roughly speaking, the distance at which correlations start to become extremely small. Because that's roughly speaking, that's the correlation length. And the problem is, to attain a physically relevant region, one needs to be able to reach a non-trivial continuum limit. And what this means is the following. In the context of this theory coupled to Higgs field, this means that the parameters G0 and lambda should be varied as L goes to infinity in such a way that the correlation length tends to infinity. And upon proper gauge fixing, the gauge field converges to a non-trivial, which in physical terms means a non-Gaussian scaling limit. Okay, so this is what people try to do when they do renormalization. So the basic condition, so it's not always clear whether there is a non-trivial limit. So in fact, nobody has been able to construct a non-trivial quantum field theory in dimension 4. So there is no construction. It's not even clear whether non-trivial limits exist in dimension 4, but certainly you need the correlation length to go to infinity. And this is what is achieved if you send G0 to 0 in a pure Yang-Mills theory. But here you have two parameters, and just varying G0 is not enough. And if you keep lambda times G0 squared large, the correlation length doesn't tend to 0. So the correlation length needs to go to infinity because it has to balance out the lattice spacing going to 0 so that non-trivial correlations are obtained in the scaling limit. And under Zeiler's condition, the correlation length does not tend to infinity even if G0 goes to 0. Okay, so the correlation length is actually 1 over lambda g0 squared. It's proportional to that. We'll see that shortly. So this does not go to zero, go to infinity, the correlation length. And therefore, you are not in this realistic regime where you're going to a continuum limit. So we'll see shortly that for the correlation length to go to infinity, we actually need lambda g0 squared going to 0. So this is the right thing to look at. And non-triviality, as I said, is a more subtle question, so I'll not talk about non-triviality because I don't know how to deal with that.
So when you speak of continuum limit, it means you don't take only bigger box, but you think that the
lattice spacing is also going to 0. Yeah, so you simultaneously have to do these two things, and then you have to ensure that this correlation length is going to infinity. So you have to vary your parameters. Okay, and then the ideal thing would be able to vary the parameters so that the limit you obtain is a field which is not Gaussian, a non-Gaussian field. And that comes from non-Gaussian fields correspond to, in perturbation theory, they correspond to theories which describe interacting particles. And if you have Gaussian, there is no interaction. Okay, so let's now specialize to SU2 theory in any dimension, coupled to a Higgs field in a fundamental representation of SU2. And you also take rho to be the fundamental representation. And you take V, the potential to be 0 if R is 1 and infinity if R is not equal to 1. So this Higgs field is just uniformly distributed on the unit sphere. And under this condition, the lattice Yang-Mills theory defines a probability measure on a configuration space as follows, where this d phi now denotes uniform distribution on the unit sphere. And SU phi is this. So there is no Higgs potential term because it has been absorbed in this. So you have phi from the unit sphere, U from from the group elements, and you just have this. And you have the fundamental representation. So it's just phi star UE phi y, and this U is now in SU2. So there's a SU2 matrix. So
what happened to V?
Oh, so the V, I took V to be infinity if R is not equal to 1 and VR to be 0 if R equals 1. So this measure e to the minus V norm x dx, it just becomes a uniform measure on the sphere. And so d phi now just means a uniform measure on the sphere. Because that's not a non-standard thing. So lots of physics papers, they do this. Sometimes it simplifies things, sometimes it doesn't. But okay. So is this so from now on in the talk, I'll focus on this particular model. Okay, so now there is this thing called gauge fixing, and I'll not talk about gauge fixing in general. I'll only talk about gauge fixing in this very special SU2 model coupled to a Higgs field in the fundamental representation. Suppose you are given the Higgs field phi. For each x, choose.
There's no gauge invariant meaning given the Higgs field.
So what?
So to give the Higgs field, it has no gauge invariant meaning.
Yeah. So what? Okay. So what I will do? Yeah. So let me go through the slide. I'll tell you what's going on. So suppose you are given this Higgs field phi. For each x, choose a theta x so that theta x phi x is E1. You can do that. So you can choose an element of SU2 so that it sends this phi x to E1. And for any edge E, you define a configuration VE as theta x UE theta y star, where theta is this. So you apply this gauge transform. So then note that trace of UP is trace of VP for any plaquette P, since V is a gauge transform of U, that you can easily verify. And the Higgs field term phi x star UE phi y, this just becomes a 1/1th element of VE. However, for a SU2 matrix, the real part of the 1/1th entry is just half the real part of the trace. So conditional on phi, the probability density of V is proportional to this. So this does not involve phi at all. So this V becomes independent of phi. And so it suffices to study a configuration V with this density. Okay, instead of studying phi, studying U given phi, and just studying V, which is obtained using a combination of U and phi, which is a gauge transform of U. And so if you're only interested in gauge invariant observables, it doesn't matter. You can as well study V. And so we say that V is obtained from U by unitary gauge fixing. So this is the procedure. It's called, we obtain V from U by unitary gauge fixing. So what you do is you take your original configuration, apply a gauge transform depending on phi. Look at phi, apply a gauge transform, and you obtain a new configuration, and then you have your V, the gauge field V, and the gauge field V will have no dependence on phi at all. So this will be independent of phi, and that's called unitary gauge fixing. Okay. So we'll study, we'll completely get rid of the Higgs. This is a nice feature of SU2 theory that you can do. You completely get rid of the Higgs field, and you study only the gauge field with this probability density. So you don't need to remember anything else that you have heard before. So you have a gauge field, and you look at just this, and you look at its behavior as lambda and G0 value. Okay.
You did buy yourself another parameter in another term, yeah.
Where?
As opposed to if you didn't have the Higgs field.
Yeah. Yeah. So this I could work because I took the Higgs field to be uniformly distributed, the base measure to be on the sphere. Okay. So now, since we are trying to pass to a continuum limit, we have to understand a little bit about what is a gauge field in the continuum. So in the continuum, a gauge field is a connection of the trivial G bundle over R to the D, which means that the gauge field is just a map from R to the D to the this Gothic G to the D, this is the Lie algebra. And suppose we approximate R to the D by a lattice epsilon times Z to the D, so a lattice with fine spacing, then a continuum gauge field defines a discrete gauge field as follows. You take this, take an edge E, which is X, and you increase the jth coordinate by epsilon, and take this edge, and you look at AJ of X, and you exponentiate that, and you get a group element. And that's the correspondence, how you get from a connection to a group element. And so we need to invert this map to get the connection. So roughly speaking, we need to do something like this. So you take UE minus I, and you multiply it by some large constant to get your approximate Lie algebra element. But I'll not go through this, so don't worry if you decide it seems a little sketchy. So what I'll do is describe an exact transformation. So it's a little problematic going through this exponential map, especially not being injective. So recall SU2 theory with unitary gauge fixing, and we are studying this probability measure on it. So we want a SU2 gauge field V with this, and we'll now rescale V to obtain a field which is to each. So actually, not lambda. This should be E. On each edge, you have a group. You have a Lie algebra element. So now SU2, the Lie algebra can be identified at R3 because each element is a unique linear combination of the three Pauli matrices with real coefficients. So it can be identified at R3. So what we'll do is actually start with a random field A in R3 and define a transformation which has this right distribution of B. Okay. So again, I'll just sketch the procedure. I'll not go into any details, but then I'll show you the main theorem, and then I will sketch the proof of the theorem, which is more important. So this procedure is not so important. Let R be a non-negative real valued random variable with its probability density proportional to this. Let Z be a random vector uniformly distributed on the unit sphere of R3. Let gamma be the probability law of root lambda times R times Z, where this lambda is a squared Higgs length. And then eta be this probability measure, okay? And eventually we'll send lambda to infinity while sending lambda G0 squared to 0. And this will make gamma tend to the Lebesgue measure, this probability law as lambda goes to infinity, and eta will tend to standard Gaussian measure. So you can think of this eta as a small perturbation of the standard Gaussian measure on R3. And then, sorry, I'm going through this a little quickly. Then you define a transformation from R3 to S3 as follows. This, and from S3 to SU2 as this, and then you take a composition of these two things, and then you can show that if you start with this probability measure, so you define a probability measure nu. Again, sorry, you don't have to follow this. So what it comes to is this. So if A is a random element with this probability measure. So this is a small perturbation of Gaussian, and this is some prefactored term. If you take a random element A from this law, then this transformation has this exact distribution of gauge fixed SU2 theory. So you have this perturbation theory that faces to work with perturbations of Gaussian and do this Feynman diagram calculations. This gives an exact correspondence between some measure on R3, which exactly translates to the measure that we're interested in. So on SU2, and you can write it down, and you will see where the perturbation terms come from. So you can exactly write it down. So this is just some calculation, but the main result is the following. So I'm still writing. Let A be a random element with law nu, and so this is the Lie algebra version of the theory. Let F1 and F2 be two functions supported on two sets that are at some distance. And suppose we have G0 go to 0 and lambda go to infinity, but satisfying these constraints. So it's going to infinity, but slightly slower than 1 over G0 squared, and faster than something a little bit less than 1 over G0 squared. So actually, it will be pretty close to 1 over G0 squared. So then there exists a tau bigger than 1 over lambda G0 squared. So tau is much larger than this factor, so that if the sets are at distance less than tau, then you have this exponential decay of correlation. So what this means, is that the correlation length 1 over lambda G0 squared tends to infinity, as you need for reaching continuum theory. And exponential decay of correlations hold at distances, up to distances much bigger than this correlation length. So you can pass to a continuum limit and have a theory which has exponential decay of correlations. And this proves mass gap. So actually, I think I know what the scaling limit will be. So it depends on the rate at which lambda G0 squared is going to 0. So I allow it to go to 0 pretty slowly. If you allow it to go to 0 pretty slowly, you will get a Gaussian theory. So you will get what's called a massive Gaussian free field. So I didn't write it down because I'm still trying to prove that, but not all the details are written up. But you will get a Gaussian free field. So if there is so any rate of lambda G0 squared going to 0 will give you a scaling limit. It'll give you a scaling limit. And there may be some rate at which, some very delicate way, if you can send it to 0, you may end up getting a non-trivial theory, non-Gaussian theory, but I'm not sure of that. But if you send it to 0 slowly enough, then you end up with a scaling limit, which is a Gaussian theory. Okay, any questions about this theorem? So, it's written in a rough way. Really what you need is, sequences of two functions and sequences of, E1 and E2 and, lambda and G0 carrying as L goes to infinity in an appropriate way. So it's not written very precisely, but this is what it means.
Sorry, why did you write it about this R3 to the E rather than just about your original Yang-Mills with the Higgs field?
Well, the thing is, so the original Yang-Mills with the Higgs field, I could have written it that way, but you'd see what will happen is that the group elements will all be close to identity. So unless you rescale them in some ways, this kind of result will not be meaningful. So what I eventually want to do is do the rescaling, get this A and have that converge to a continuum limit, continuum theory, which is a free field. So you take the group element subtract of I, multiply it by an appropriate scalar, and then you will get a real valued field, which R3 valued field, which will converge to scaling limit. So I could have written it the other way also.
When one speaks of continuum limit, how rough would the connection? You said that the picture is a G bundle with a connection.
Yeah.
But
the connection.
Irregular.
Oh, yeah. So it will be as irregular as a Gaussian free field. So it'll be random distribution. So the Gaussian free field, I'm forgetting exactly what is its irregularity, maybe h to the -1 or something like that. So it'll be very irregular. Yeah, very irregular, and it'll get random distribution. Okay, so let me tell you a little bit now about the proof idea. How the basic crux of the proof, not any technical details. So this even if you haven't followed this transformation and so on, it doesn't matter. So I'll work with with the gauge theory. So, so for a technical reason, I'll consider periodic boundary condition here now. Let sigma prime be the subset of sigma consisting of all u which are close to I. So, and each coordinate, it's within 1/root lambda of I, okay, very close. So the normalized Haar measure of this is of order, lambda to the minus 3/2 times the number of edges, because, remember the Lie algebra is three-dimensional. So a ball of root lambda will have, radius root lambda will have measure lambda to the minus 3/2.
Is it the same lambda as before?
Yeah, it's the same lambda. It's the same lambda, the Higgs length, a squared Higgs length. So it's lambda to the minus 3e to the by 2. Now the probability measure mu defined by the gauge fixed theory as a measure with density proportional to this. So remember I had this real part of u times something, but it's the same as u minus I squared, because if you take any SU2 matrix, u minus I norm squared is just some constant plus the real part of the trace of u. So you can write it like this. And the nice thing is that both these terms are now non-negative. So this kind of measures how far these are from the identity and how far these are from the identity. And this coefficient is much bigger than this coefficient because lambda g0 squared is close to 0. So this is the dominant term. So now if u is in sigma prime, u satisfies this, that all of these u's are close to lambda minus I by lambda minus half. Then these terms are all of order 1/lambda, right? So this pu is greater than or equal to e to the minus L to the d over lambda g0 squared, assuming that this is less than or equal to 1. Okay, so if you have a special configuration in this set where all the coordinates are very close to identity, you will have this density bigger than or equal to e to the minus L to the d over lambda g0 squared, right? Everyone agrees with this? Okay, because these are of order 1/lambda and the number of terms is L to the d. So combining, we get this. So in this region, you have this lower bound, and this region has measured at least this. So you get this lower bound, e to the minus L to the d over lambda g0 squared, lambda to the minus L to the d. So the normalizing constant of this measure, the integral of pu, is at least this, right? What this means is that if you take 1/the normalizing constants, it's at most this. But 1 the normalizing constant, the one you can write is the integral of pu inverse pu du. So it's the expectation of pu inverse. So that is bounded by this. So now you take hu to be minus log pu, which is just this term. And combining, we get that for any t positive, the expectation of this indicator, so this is a random variable, there's a function which is 1 if hu is bigger than t and 0 if hu is less than t. So that's very standard notation that we use in probability. So this function, which is 1 if hu is bigger than t, so this is the same as pu inverse is bigger than e to the t. And then by Markov's inequality, that's bounded by the expectation of pu inverse over e to the t. But the expectation of pu inverse is bounded by this, we know. And so therefore you get this bound. This expectation is bounded by e to the minus t, e to the c1 L to the d lambda g0 squared, lambda to the L to the d. Everyone with me on this slide? So I in the previous slide, I showed that pu is lower bounded by e to the minus this on the region where all the u's are close to identity, and that region has measured at least this. And so therefore you get this bound, and that's the expectation of pu inverse, the expectation of the inverse of the probability density under this measure. And then you take h to be log of this pu, which is just this, and you get this bound, okay? But also this is less than or equal to 1, obviously. It's the expectation of a random variable which is at most 1. So you get the expectation of hu is the integral by Fubini's theorem, this integral of the expectation of indicator hu bigger than or equal to t dt. This thing is bounded by the minimum of this and 1. And when you integrate this, 1 dominates until t reaches this threshold, and then it decays sharply. So you just get this threshold. So you become, the expectation of hu is bounded by constant L to the d over lambda g0 squared plus some constant L to the d log lambda. But HU, if you look at the formula for HU, it's this plus something positive. So it dominates this term. And by symmetry, this is where I need the periodic boundary. This expectation is the same for all E. So due to the periodic boundary. So I'm taking the theory on the periodic boundary. So the expectation will not depend on the edge. It's the same for all E. And therefore, you obtain this key estimate. If you plug this into this bound here, you get that the expectation of norm of UE minus I squared is bounded by constant over lambda squared G squared plus constant log lambda over lambda. And the key thing here is that this is no dependence on L. So you see, L does not depend at all. L is not involved in this at all. And that, is the key thing that you get from this argument. Okay. So with high probability, if this side is small, with high probability, U is close to identity without a dependence on L.
We must have, but with a few exceptions.
Yeah, with a few exceptions. So yeah, so I'm coming to that exactly. So now, suppose B is the cube of width tau inside lambda, then the maximum deviation of U from I within this cube expectation is bounded by sum of these expectations, obviously because maximum is bounded by the sum. And therefore, now you can plug in this tau to the D factor, so it's this earlier bound multiplied by tau to the D. And now you see that if lambda is between these two things, it's much less than 1 over G0 squared, but much bigger than something that is close to 1 over G0 squared, but not quite, a little bit less. It's possible to choose a tau in that case. So explicit choice is given by this. It's possible to choose a tau which is much bigger than 1 over lambda G0 squared, and yet this goes to 0. Okay. So it means that this allows us to take lambda G0 squared to 0, but at the same time have UE converging to I everywhere within a box of side length much bigger than 1 over lambda G0 squared. And once we have this, so I'll stop here. The rest of the analysis, you now have perturbation around the Gaussian, so you can carry out this analysis. Okay, thank you.
Questions? I've got a question and a comment. First question, you come here and you're showing Ed Witten. How close are you to the $1 million problem? Now, what's that question? You ever looked there? And then I've got a comment for you. What is it formulated? What do they want there?
Okay, so let's see the best I understand. So what they want is that they're in the problem statement itself. They are not doing the Higgs potential. They're looking at pure theories. Pure Yang-Mills theory. You have pure Yang-Mills theory. You want to find a continuum limit which is non-trivial in the sense that, as I said, this correlation length will go to infinity, and the limiting field that you get after some proper gauge fixing will be a non-Gaussian field, and it will be gapped. Okay, so this is what you want. And that's I think that is the problem. Now the thing is, eventually you would have to construct quantum theory. There is a prescription for doing that, starting from a Euclidean, this statistical mechanical theory to get a quantum theory using these Weissman axioms or the Osterwalder Schroeder axioms. But I don't think those quite apply for this Yang-Mills theory. So you have to find some variant of that which can give you a quantum theory, which is basically this, you have to find a quantum Hamiltonian and show that it is gapped.
And now a warning to you.
Yeah.
You must read the fine print of those. I mean, I'm sure you're not so worried about what's in the fine print, but it says to be paid your $1 million, you must prove everything. If you disprove anything, they have the right not to give you the money. In particular, if you disprove the Riemann hypothesis, then they're not paid. So, you read the fine print. Anyway, that's a joke.
So what feature of the Higgs representation did you use here?
Well, so one of the things that I'm using here is this unitary gauge fixing, which is kind of special to SU2, that you can do that. That is, you can completely get rid of the Higgs field and work with a combination of the Higgs field and the gauge field, which has a nice distribution.
Okay. SUN does not do this.
So SUN, I don't know of a direct way of doing this because you see, the thing is, Okay, so you still can have, so let me go back.
You can still get fixed. And
You can still do that, but there is one problem. So I'll show you what's the problem. Yeah, one thing doesn't work. Okay.
or the one that
Did I go ahead?
I'm using
the fixator should be small.
it doesn't depend on the sun.
No, so yeah, so here it is. So you can reach up to here, but this is the special thing about SU2 that the real part of the 1 at entry is the real part of the trace. So if the 1 at entry is close to 1, the whole thing is close to identity. That's not true for a general SUN.
What is the philosophy about the non-Abelian nature of G? What's it supposed to impact sort of dramatically?
So with the Higgs field, it's not particularly important about the non-Abelian feature. What they say is that for SU3, for instance, in 4 dimensions, even without the Higgs field, you should get a mass gap. And that's where the non-Abelian comes in, because with U1 theory in 4 dimensions, you at weak coupling, you don't get a mass gap. Okay, so that's
supposed to.
Yeah, and no one knows how to justify that, even in a heuristic way.
Other questions?
Did I understand correctly? The picture is that choosing the constant 12, you can somewhat pretend that all the UI are small and computation works as if they were small.
Yeah. So they're all close to identity, and then you can do a Gaussian expansion, and then But the thing is to show that this thing can be done independently of the size of the full thing, because that's not clear. You see, this coefficient is much bigger than this one, so this can completely override the other one, and so it's not clear that it'll force things to go to the identity.
Okay, let's thanks Sourav again.